You're cut off by the horizon, so you say, okay, let's go and travel to the horizon. Boy, you can keep going, and you don't make any impact on the size of the universe. So the effect about this is that it's like trying to tell what the Earth is like from the top of a sand dune in the Sahara Desert, and you look around and you say, wow, the whole universe is made of sand dunes. Well, that's because you can't travel to the other parts because the scale is wrong. This little ant sitting there comes up with the theory of the Earth is made of sand dunes, and it follows exactly the lines of the argument which I've given here, the Copernican assumption. Everywhere else must be what you see. Well, you can immediately see it ain't necessarily so. Okay? So although the bit of the universe we can see has got a particular kind of structure, the part of the universe we can see is limited to 10 to the 10th light years. And way out here, things could be completely different. In fact, chaotic inflation makes the claim that they are completely different out there. All right? So when we look at this business of the size of the universe, it raises a question of why, but it raises an enormously important question for observational cosmology. It's telling us the limits on what we can know about the universe. We can only know what is inside this little sphere. When I say little, 10 to the 10th years, compared with an infinite universe, that is a zero fraction. Compared with very, very large universes, that is a tiny fraction. I return to the small universes. The exception is the small universes. If by chance we were in one of those universes we've already seen around, then the situation is completely different. Then we have seen everything in the universe. Not only seen it, we've seen it multiple times. And in that case alone, we have complete observational access to everything that there is in the universe. You can begin to see why I say it's a really important question. Is the universe a small universe or not? It really makes a huge difference to our relation to the universe. Okay, on a slightly different kind of point about the size of the universe, people have continued to ask why it is so large, and the answer which is given today again is the same. It is the inflationary universe which has made it so large, as you're going to hear in other lectures in this course. And on the other side, I mentioned life briefly, the existence of life, of course, from a sort of human perspective. One finds here the incredible smallness of humanity in terms of relation to the universe as a whole. Now, as a cosmologist, one could have imagined a universe which is only 1,000 light years across, or was only 1 light year across, or a fraction of a light year across. Thinking of the family of all cosmologies, it is a very important feature of the universe that it is as big as it is. It could have been very small, and it ain't. Okay. Now, evolution of matter in the universe is section 4. I'll carry on for about till about 1:15. I think you'll be pretty tired by then. Okay. In a Robertson-Walker model, you have the pressure, which is a function of time, and the energy density, which is a function of time. And what you need in order to describe the matter is equations of state. Equations of state relating the matter to the radiation. For instance, pressure is 0, which nowadays is called baryonic matter. Or pressure is a third mu, radiation. Now, what kinds of matter must we take account of? And this is really important. Cosmology is really tied into physics in a crucially important way. Okay, we know we've got baryonic matter. We know we've got radiation. We've got neutrinos. We've got cold, dark matter. There's a lot of evidence for that, which I'll mention a bit later on. We've got a cosmological constant. There's a question whether you should think of the cosmological constant as matter or not. But what you may have is scalar fields. That's a field phi, and associated with it may be a potential v of phi. And it is scalar fields which underlie the theory of inflation. So we better take them pretty seriously, because they are what dominates the very early universe if inflation is correct. So we've got baryons, we've got photons, we've got neutrinos, we've got cold dark matter, we've got scalar fields. That's a minimum that you need to take into account in a realistic look at matter in the universe. Actually, of course, it's much, much more complicated than that. You've got quarks and anti-quarks. But at the cosmological scale, we don't have to go into those details. We can use a phenomenological description in which we don't discuss the fundamental nature of it. We just use a large-scale approximation. Now, the two approximations, one is the kinetic theory description, and the other is the fluid description. In cosmology, we either use a kinetic theory or a fluid description. And I'm not going to go into the kinetic theory description here, but it's become very important in analyzing the cosmic background radiation. And if you go seriously into cosmic background radiation, you better learn kinetic theory on a curved space-time, which is quite a fun subject in its own right. But we'll use the fluid description, which is the continuum approximation. Now, when is a continuum description a good description? Well, you need a sufficient number of particles, is the first point. Sufficient numbers of particles, and I've said we've got about 10 to the 11th galaxies in the observable part of the universe. Is that enough for a fluid description? It's actually very marginal. In 1 cubic centimeter of matter, there's 10 to the 23rd atoms, much, much, much bigger than that. If you're talking fluid descriptions, this is really on the very low side for a fluid description to be good. On the other hand, the other alternative would be an individual particle description. You try to describe every particle in some sense. Well, that's hopeless with 10 to the 11th, so we certainly won't try that one. So we will use a fluid description, but remembering, actually, the statistics are not that good for a fluid description with only 10 to the 11th. The next thing you need is regularity. And what I mean by that is the following. Supposing you take a box of size L and you measure the density in there. Well, it's a function of the size L. And there are different possibilities. What we need is, what happens for a realistic fluid as you vary the size is something like the following. On large scales, it's smooth, but on smaller scales, it starts fluctuating. Now, why does it fluctuate? Well, very simple. For a small enough box, as you change the size of the box, the number of particles in the box becomes just a few atoms, and each time you get 1 or 2 more atoms in, you get a wild fluctuation in the density of the box. So you need to be much, much bigger. You need to have a large number of particles in there in order to get this smooth description. At large scales, it starts varying because of macroscopic variations, and so there will be a set of scales on which a fluid description is a good description. I keep coming back to this idea of an averaging scale. So in cosmology, the idea is that there is a set of scales. Now, there are some universes in which there never is such a scale, and those are fractal universes. So the practical question we're being asked is the universe in fact fractal? And you will have seen many books out there saying, yes, the universe is fractal on all sorts of scales. If the universe was fractal on a cosmological scale, life would be very, very difficult for cosmologists. Now, there is a group of people who say it is fractal on that scale. There's a group of people in Rome who keep producing analyses who are saying, yes, it is fractal. However, most people believe it may be fractal on smaller scales, but by the time you hit this kind of averaging scale, that the universe is smooth. And that is critical in defining this 4 velocity. You can only define a 4 velocity if the universe has got a good averaging scale. Otherwise, the fluid description isn't possible and the averaging scale description doesn't hold. So, we will assume that it is not fractal and that a fluid description is good. Then we can use a stress tensor, rho UA-UB plus P HAB, where H is the tensor GAB plus UA UB. And that is the stress tensor for the fluid. Now, You put that into the conservation equations, and in this brief series of lectures, I don't have time to do the mathematics. You'll have to believe me, what we get out of that is the conservation equations. Rho dot plus 3, rho plus p, a dot over a is 0, that is energy. And the momentum equation will be naught is naught. It's identically satisfied. So in the context of the standard model of cosmologies, there is only one equation which matters for energy and momentum conservation, but it's exceedingly important. It is the equation of energy density conservation. Now, what you can do with this is you can put in some of these equations of state, like that or that, and see what happens. So, for instance, if you put in P as naught, you get rho dot plus 3 rho A dot over A is naught. So rho is a constant over A cubed, and that is conservation of baryons. If you put in P as a third mu, then you get rho plus a third rho, and that gives you a rho dot plus 4 rho A dot over A is naught, and you get rho is m over a to the fourth, and that's conservation of radiation. And the difference is very, very important. The difference comes from the p in the rho plus p there. As I say, I haven't got time to derive these equations, but that's what you get. Now, for radiation, rho is a constant times t to the fourth, and so put that together, the temperature is proportional to 1 upon a. One of the fundamental features of the expanding universe, as it expands, the temperature scales inversely with the radius. And so that's one of the absolutely fundamental things that happens in the expanding universe. For radiation, temperature goes down as 1 over a. And that underlies the whole hot Big Bang. Because, as I've already mentioned, we've got 3 degrees K radiation today. We'll follow the universe back. Well, when it was 1,000 times smaller, it was 3,000 K. When it was 1,000,000 times smaller, it was 3 million, and so on and so on. And so we have the hot Big Bang, follow the universe back. As A goes to naught, the temperature goes to infinity. And that is why all of fundamental physics comes into play as we follow the universe back to earlier and earlier times. Following it back, you get nuclear physics, particle physics, quantum gravity. They all come into play because of the conservation equations here. Now, what is very important is energy inequalities. And the one which I'll point out to here, for any ordinary matter, rho plus p must be positive. The energy density plus the pressure must be positive. Now, for ordinary matter, the density is positive and the pressure is positive. But we're going back to the very early universe when extreme quantum conditions were in control, and things could have been very, very different when those extreme quantum conditions were in control. The limiting condition is rho plus p is naught. Now, what happens if rho plus p is naught? Well, what happens is very strange. Look here. In that case, it doesn't matter how you expand the universe, then rho dot is naught, rho is constant, irrespective of whether the universe expands or contracts. So if you could ever find matter with rho plus p 0, it wouldn't be affected by expansion or contraction. Well, what is that? That is, in fact, the cosmological constant. Supposing you could find matter with rho plus p less than naught, what would happen then? Well, something very, very odd indeed. As you expanded the universe, the density would go up instead of going down. Not only that, but the momentum equation for perturbations would tell you. The momentum equation actually in general will be that dv by dt plus rho plus p times the, rho plus p dv by dt is equal to minus the pressure gradient. I'm writing it out in a rather cryptic notation. In relativity, the momentum equation is rho plus p dv by dt is minus the gradient of the pressure. And if you could find matter for which rho plus p was less than naught. What would happen because of this equation